Now let's flow in all the data science into the building and get entertained and excited about our first speaker. Since Industry 4.0, we talk about cyber physical systems. Most people didn't talk much about security issues about that. Ensuring the security of cyber physical system has become an urgent and vital need. To address this issue, Sophia will present a deep learning-based anomaly detection which exploits 2D representation of a network traffic. So please welcome with me on stage, Sophia Casarin.
Thank you.
Sophia is a research fellow at University degli Studi di Padova. It's just outside a very beautiful town outside Venice. So the floor is yours. Really excited.
Thank you. Hi, everybody. I am Sophia Casarin from University of Padova. And today I will talk about our work entitled Unsupervised Network Anomaly Detection by Learning on 2D Data Representations, a paper that links network security and deep learning. So let me first give a general framework of what we are talking about. We are talking about cyber physical systems. So a cyber physical system, shortly CPS, can be thought of as a combination of digital, analog, physical, and human components that interact together to provide a specific service or a function. CPS is applied in many areas that go from power system to traffic management to personalized healthcare. And as its role is increasing in our society, reliability and security become of primary importance. Therefore, to detect discrepancies from the expected behavior, several anomaly detection methods were proposed in literature. But as they require much expert knowledge, they were recently replaced by machine learning-based approaches. Anomaly detection can indeed be addressed by different deep learning strategies. And in our paper, we decided to follow the generic normality feature learning strategy, which is an approach that exploits the generalization ability of deep learning to detect anomalies. What we did was training a rational autoencoder to reconstruct data, real traffic data, by focusing on network-level security issues and adopting a 2D representation of real traffic data that was previously proposed in the state-of-the-art. What is new with respect to previous approaches is that in the literature, only few works elaborate traffic through 2D representation and exploit deep learning. Among them, the majority is focused on malware classification, which means supervised learning and costly labels, and not on anomaly detection. And the few CPS existing work are based on sensors measurement and not on network traffic. So our work is new because we elaborate traffic data in images and exploit deep learning to perform anomaly detection. As a dataset, we employ the UGR16 dataset, also following what the dataset that the authors of the 2D representation used. This dataset is generated by collecting real traffic from a tier 3 of an internet service provider and by injecting simulated anomalies. It is divided into a calibration and a test set. The calibration is made only of real traffic data, while the test set has both real background traffic and anomalies. The UGR16 dataset originally had 3 types of anomalies. It has denial of service, port scanning, which is shortly scan, and botnet attacks. But as the authors of the dataset did not account for, the effect of botnet over normal traffic, and also as the authors of the 2D representation discarded this anomaly, we kept only those 4 types of anomalies in our test set, which are DOS11, DOS53, scan11, and scan44, where the first number stands for the number of attackers, and the second number stands for the number of victims. As an image we generated the image dataset following the approach proposed by Baldoni and her colleagues that I'm summarizing here. What they did to the UGR16 dataset was, for each time window of fixed size 1 second, they elaborated the dataset by computing the number of bytes sigma exchanged between a source node I and a receiver node j. Then they computed the mean, mu ij, and subtracted it from sigma, obtaining sigma mu. They further divide sigma mu by the standard deviation of the number of bytes, plus a small term to avoid division by 0. And they finally multiply this variable, sigma mu sigma, by an exponential function of the number of flows exchange between a source node I and a receiver node J, obtaining sigma mu, sigma E. That I'm showing here in this figure. This is a matrix representation where over the columns we find the destination IPs and over the rows the source IPs. As you may observe, we have huge intensity values for the pixel, and indeed, this representation is not suitable to be processed by deep learning algorithm up to this point. So what we did was adding a further step that consists in performing a mapping that separates background traffic and anomalies in different portions of the image. Moreover, we define a binary mapping that sets to 1 all the pixels that have an intensity different from 0. And we call this representation M, that is shown here. As you may observe, on the left side, we have an example of a background traffic image, and all the pixels related to background are mapped in the upper rows, while on the right side, we have a scan image, and we have the pixel that is mapped to lower rows. Once we defined all the steps, we generated the image dataset and split it into train, test, and validation, as is commonly done to train deep learning algorithms, following the assumption of anomaly detection algorithms, which is that the train set is composed only on anomaly-free data. So, as you could see, the images are quite peculiar with respect to the most known dataset as Cypher10 or ImageNet. And we were particularly quite concerned about the majority of black pixels. So what we did to have a full comprehension of the dataset was analyzing the distribution of the active pixels by counting how many images have an active pixel over a specific location. And we obtain that distribution over there, where you can see that we have a gap before the destination IP 100. This, unfortunately, is an intrinsic bias of the dataset, does not depend on the 2D representation. And it's due to the fact that over the recording period, those IP were not communicating. But we were afraid that the algorithm, rather than understanding that an anomaly is when we have active pixel in the lower rows, might understand that an anomaly verifies in that region. So to mitigate this bias, we employ the integral transformation that performs a cumulative sum over the rows and helps giving more relevance to the vertical distribution of the active pixel. Moreover, it reduces the dependency of the loss on the specific location or specific horizontal location of the IP. So here I show you an example. I believe that you might struggle in finding the anomaly on the left-hand side, and the network, of course, has the same problems. So instead, as you can see, the integral transformation kind of propagates the pixel over the right side, mitigating the gap in the 100 region before the 100 destination IP, and giving more relevance to the IP as well. So, as an anomaly detection strategy, as I said, we trained a variational autoencoder over anomaly-free images. In this way, the variational autoencoder is trained to learn the normal distribution of data, and when it's employed to the test set, more precisely on an anomaly, it fails in reconstructing the image, which means that we can detect an anomaly if the reconstruction error is bigger than a certain threshold tau that depends on the mean and the standard deviation of normal images. So we employ the architectures with the 2D representation, keeping in mind two goals. We wanted both to achieve a competitive true positive detection rate and limiting also the false positive rate. As we couldn't compare our work with other papers because of the fact that our representation is kind of new, we decided to, together with training the variational autoencoder, both with the M representation and the integral representation, also to employ a simple deterministic algorithm that consists in setting a threshold and to detect pixels lying above or below the line. As it is super fast, we ran the algorithm multiple times by varying the threshold and use the best result as a baseline to compare the results of the variational algorithm. So the architecture consists of an encoder module and asymmetric decoder modules composed of 6 layers. We have that downscaling is performed through max pooling 2D, and upscaling is performed through transposed 2D convolution. The number of filters is variable in the layers, and we chose both the number of filters and the number of layers through an optimization procedure that we performed with Optuna framework. We trained the variational autoencoder with this loss, that is a combination of a reconstruction loss and the Kullback library divergent that acts as a regularizer, and use the reconstruction loss, the binary cross entropy, and setting the gamma value empirically equal to 0.3. From the point of view of the experimental setup, everything was implemented in PyTorch, and the experiments were run on a workstation with NVIDIA GeForce 3090 GPU. The hyperparameters were again optimized with Optuna. I will skip the details of the numbers. And we evaluated the measures in 4 different ways, by using precision, F-score, and by using 2 measures to understand how far or close we were from the goals, which are the recall, also known as true positive detection rate, and the specificity, also known as true negative detection rate. Here I show you the results. So on the first 3 columns, you can see the results of the deterministic approach. I reported just the extremes and the middle value. You may observe that the smaller the tau d, the higher the number of true anomalies that are detected, while the larger the tau d, the higher the number of true background traffic that is detected. This might look a silly consideration, but actually it is not, because as the 2D representation was kind of under test phase, these results show that it is working, because of course the more the line goes down, the more background we detect, true background we detect. So to balance our 2 goals, that are the recall and the specificity, we chose as best result the tau d equal to 30, that we will compare with the variational autoencoder. You may observe that although it gives satisfactory results for the recall, we still have big room of improvements for the specificity. So, going now to the variational autoencoder, we trained it again with a binary cross entropy loss, where we also applied a mask. This mask basically weights every 1 intensity pixel by a factor W equal to 10. And we did it because our concern about the majority of black pixels was actually confirmed by the fact that in the beginning, the variational autoencoder tends to overfit by reconstructing all black images. And so we kind of helped it by giving more relevance to the 1 intensity pixels. So, from the point of view of the results with the M representation, we got an improvement of 4%, more or less, in the number of true negative detected, and of more than 1% in the recall rate. This is justified by the histogram on the right, where you can observe that the reconstruction error of anomalies and the reconstruction error of clean images have different values, as we would like to have, but unfortunately intersect for 15.6% of the area, which is the reason for the still left 3% of false positive. As we were not happy with this result, we analyzed what was happening in the images that were detected as positives, and we found out that unfortunately those kind of images, in most of the cases, were images with active pixels in the prohibitive region. So, moreover, we also studied the left undetected anomalies and realized that all those 6 images were images with very few active pixels, which, although the attack-related pixel is not reconstructed, unfortunately, it does not impact much on the reconstruction error, which is the reason for which it is not detected. So to mitigate this issue and the other one, we employ the integral transformation that gives the best result. We get an improvement of 2.65% with respect to the M representation, and of more than 6% with respect to the deterministic approach. Moreover, we are able to reach 100% in the recall rate, so we can detect all the anomalies, and indeed now the values of the reconstruction error of anomalies and clean data are very well separated. Last thing we needed to do was understanding how the images that were detected as positive, because we have still a small percent of images that are detected as false positive, looked like, with the goal of improving the 2D representation. And we realized that those false positives are detected as such not because of problems in the variational autoencoder, but because of some imperfection in the 2D representation. Indeed, you can see that on the left side, the image has an active pixel in the lower rows, and it is not reconstructed correctly. But unfortunately, this is a background image. So even though the 2D representation works well, we still need to improve something to have a better separation in background traffic and anomalies. So to conclude, what we did was proposing a deep learning algorithm based on a variational autoencoder to detect anomalous behavior in CPS system based on 2D representation of real traffic data. We trained the model considering clean background images and the corresponding integral representation, and compared the results with a deterministic algorithm that is able to also access the quality of the 2D representation that we proposed. We proved the advantage of employing the deep learning algorithm with respect to the simple deterministic approach, together with the effectiveness of using an integral transformation with this kind of images. Thank you.
Thank you very much, Sofia. So from Italy, but perfect on time. Thank you. This gives us plenty of time, 5 minutes for questions. So you just raise your hand. I start with an icebreaker, of course. So it's amazing results. It looks pretty nice. I mean, it's security, it's 2D representation, it's deep learning. How did this work out? How was the task? What was the most difficult task in such a project?
So the original task was actually proving and determining if this 2D representation was working. So the tough part was understanding this kind of data, because of course the person behind the network security part had in mind how anomalies work, how true data work, but we were not sure that a deep learning algorithm could detect these tiny differences, because this is more a defect detection rather than an anomaly detection, which is a tough task. So detecting, working with the kind of images was the complex part, probably.
And the deep learning part was quite easy.
Kind of.
Are there any questions from the audience?
Yes, thanks. Thanks for the talk. I have a question. So you used only the reconstruction error. What is with the latent space?
What's
the latent space, so the embedding. Can you use this for detection using local outlier factor, and how is the results then?
So yeah, we also tried to perform classification in later works over the latent space. And actually, the latent space is well separated in most of the cases. I don't know if that's the question. We could see that we have, it's quite well disentangled, mostly thanks to the gamma value in the loss function. But still, we have kind of overlapping between the scan attack and the background traffic. So, but we believe that is due to the representation again, because of the representation depends a lot in the number of flows. So in further works, we will try to refine it and also perform classification in the latent space. I don't know if I answered your question.
More questions? Thilo, you always want to have a question, come on. No.
I was wondering what the original intuition was to use convolutions in the network architecture, because the inductive bias there is to be completely translation invariant. And I figured from the data that the position where the, let's say, pixels occur is somehow important. So this somehow, to me, it sounds counterintuitive to use a convolutional architecture.
Well, we used a convolutional architecture because we wanted to keep the 2D representation. So we wanted to keep, the structure, the geometrical structure. We try also to employ fully connected networks or to flatten the layers, but we lost the information, the geometrical and the structural information of the images. We could have elaborated the data in many other ways, also by using the raw data, of course. But as the main goal was proving the effectiveness of the 2D representation and on the location, we decided to use convolutions, basically. That's why.
Thank you.
You were training on a GPU 3090 GeForce. Can you elaborate a little bit on the training times, training, validation, inference time?
Yes. So, well, optimization took a while because Optuna is fast. It's a framework that basically performs different kind of searches to look for the algorithms and for the structure. That part took a while. From the point of view of the training, 3090 GPU is super fast. So it actually took roughly 2 hours and a half after optimization of the algorithm. So quite fast, I would say. Also because the images are big, and we were afraid that having these huge images with this many black pixels would have been a waste of time. But actually it is fast, so it was okay.
And what would be now needed to put this in a real-world life environment?
Yes, but we would like, first of all, to, before setting a real-life environment, we would like to include also the botnet attack, also to see how the representation works on those kind of attacks, which are, of course, should be considered. Also because the representation was built for DOS and scan precisely, so we should first assess how it behaves with different kind of anomalies, and then probably, yeah, we could employ it somewhere.
Perfect. A last question? Otherwise, thank you very much, Sophia.
Thank you.